So first of all, yes, I can have them back Monday. Sorry, but they will be back Monday. So first of all, lab tomorrow. We are going to do the intuition post-test. If you remember, you did like a bubble sheet pre-test at the beginning of the semester. We're going to do that. That'll take about half an hour. And then after that, there's not going to be anything else going on in lab except I'll be there to answer questions. If you want to stay and work on stuff, you can. I'm not going to take attendance beyond just taking that post-test. Oh, for the post-test, if you take it, I'll give you +1 point on an exam.
Like if we take it, then we get like one extra credit point?
Right.
Oh, yeah.
Just to make you all come, just to encourage you all to come. And then after that, it's just, I'll be there for questions. You can ask me questions about labs, about homework. You can work on homework with each other, whatever you want to do. So yeah, or you can just take this post-test and leave. That's fine with me too. And then we have one more lab after that. So lab on Friday, the 10th. Is lab exam 3. I think I just started to spell lab exam with an F. Okay, lab exam 3. Anybody have any questions about that?
I have a question about the lab exam 3. Basically, we did like potential energy and everything that we did.
Just everything, yeah. Everything we've done in the labs. Yes?
Will we get to know our scores on the English test?
Yes. All I have to do, yes, I need to make out a new answer sheet and then just plug it through a machine. So I'll get all of those, the pre-test scores, the people who don't have the pre-test scores yet and the post-test scores, I'll get them both up before finals week. Yes?
What is the punishment for getting less on the post-test?
It's a punishment for me. I'll never forgive myself. Sometimes it happens, like if people get really high scores on the, usually people who've taken a lot of physics in high school or whatever, people just rock the pretest. But then there's always a little bit of wiggle room in the, and so if there's not much room to improve the concepts and you happen to get lucky on a couple, then you can get a lower score on the end. It's happened before. I just cry myself to sleep for a little while and then I'm fine.
Wait, is post-test grade if you are
Nope. Nope. It's just for me. Because I'm just trying to figure out ways to get these sort of intuitive concepts built into the sort of mathematical stuff that I have to teach to get you ready for the next levels, Any other questions? Okay. So finally, so I'm going to skip answering homework questions today, but I'd be happy to answer homework questions as much as you want in lab tomorrow. So finally, the moment equation, aka the rotational version of Newton's second law. N2L, aka M equals I alpha, aka tau equals I alpha. Okay, different people call it different things, but these all refer to the same equation. And that equation says, well, I've already brought it up before, add up all the moments about A, so MA net is equal to the mass moment of inertia about A times the angular acceleration, where A is either fixed in the inertial coordinate system or the body's center of mass. Okay, so if the body has a point that's fixed in the coordinate system, then use that. It's easier to do the calculations. If it doesn't have a point fixed in the coordinate system, then you have to use the center of mass. And one thing I want you to know is I'm writing this as a scalar equation. But it's really just the z component of a vector equation. And that's because we're doing all our calculations in 2D. All of this stuff is for 2D only. Anybody have any questions clarifying that? Okay, so I'm going to list out a set of steps that you can follow. If you can do it without the steps, feel free. I don't care if you follow these steps, but it is a nice way to make sure you don't forget anything. So steps for rigid body kinetics. And if you follow these, it'll always work. Okay, so the first thing you have to do is, does the body have a fixed point? Is there a point on the body that's fixed in the coordinate system, like a hinge connecting the body to the wall or the floor or something? If yes, then the about point A is the fixed point. If no, then the about point is the center of mass of the body. Second, calculate the mass moment of inertia. So this is I sub A. If the about point A is the center of mass, then you don't have to use the parallel axis theorem. All you have to do is use the formula. If the about point is not at the center of mass, then you will use the parallel axis theorem. And that means that the mass moment of inertia around your about point, I sub A, is going to be equal to the mass moment of inertia about the center of mass plus the mass of the body times that distance squared. Okay, remember talking about that if you're dealing with an axis of rotation that's not at the center of mass, then you add on this term md squared, where that d is the distance from the center of mass to the about point A. Okay, so now we have the mass moment of inertia. Third, draw a free body diagram. Yes?
In the first one, you said if A is the center of mass, no parallel axis theorem, just formula. Can you specify that?
What the formulas are? The formulas, I gave you a list of 3 common shapes. We're not going to do any complicated shapes, and they each had a formula for a moment of inertia about the center of mass. The slender rod, the rectangle, and the disc. Yeah, so if there's no fixed point, or if the about point is the center of mass, you just use that formula directly. Fourth, calculate the moments produced by the forces in the free body diagram about that point A. Five. Now, sometimes you'll use this and sometimes you won't. If there's no fixed point, then use Newton's second law. And Newton's second law says add up all the force vectors in the free body diagram. That's equal to the mass of the body times the acceleration vector of the center of mass. If there is a fixed point, just skip that. So you won't have to use Newton's second law if there is a fixed point. If the thing is connected to the ground by a hinge or whatever, just skip this. So this one's in parentheses. Maybe you use it, maybe you don't. And then 6 is the moment equation. And it says add up all the moments you calculated, the sum of those moments, the net moment about A, is equal to the mass moment of inertia about A times alpha. And then the last thing is 7, you'll often need to do this. It's not necessarily required, but often then you'll need to calculate the acceleration of some point on the body. And then you can use relative motion and or circular motion to calculate the acceleration of other points on the body. Of points on the body. Okay, it's a lot of steps, but as I go through the examples, I'm going to just follow this set of steps. It'll keep you from missing anything important. Any questions before I do the first example? Okay. So let's say there's a hinge connected to the wall and a rectangular shape connected to the hinge. And let's say that the lengths of this shape are 0.2 meters and 0.4 meters. And the mass is 2 kilograms. And let's say we want to calculate the acceleration of this, excuse me, of this point. Let's make that B. So what's the acceleration vector of that point B? And let's just go through the steps one by one. So the only force acting on this besides whatever's happening at this joint here is gravity pulling it down. And the weight acts at the center of mass always. There is a force. This isn't touching the wall. It's only touching the hinge. So yeah, there's actually at that hinge, there's a totally unknown force vector because it won't let that thing move vertically or horizontally. So we'll just put that in as like an unknown vector R. We'll see that in this, it doesn't even come into the calculation. Okay, so first of all, step 1, does this have a fixed point? Yeah, so fixed point. So the about point is at the hinge. And next we have to calculate the mass moment of inertia. So the mass moment of inertia at A is equal to, do we have to use the parallel axis theorem on this? We, 50% chance. The only time you don't have to use the mass moment of the parallel axis theorem, sorry, is when the about point is the center of mass. This one, the about point is that hinge over on the left and top, so we're going to have to use it. Okay, so IA is equal to I around the center of mass plus MD squared. And if you look at the formulas I gave the other day, the mass moment of inertia about the center of mass is 1/12 times the mass times the length squared plus the width squared. So 0.4 squared plus 0.2 squared. And then we'll add on to that the mass, 2 kilograms, times the distance squared. And the distance is from the center of mass here to the about point. And so if you think of that as, make this into a right triangle, we're trying to figure out the length of that hypotenuse squared. So that's just going to be 0.2 squared plus 0.1 squared. Oh, okay. Anybody have any questions about where I got any of that? Could someone punch that into a calculator? .1216. Okay, thanks. And the units, we have a mass times the length squared, so this is kilogram meter squared. Step 3, what's step 3? Yeah, because this is the distance squared. So the distance is the square root of this, and then you square it, and you just get those squared. Any other questions about where we are yet? Okay, step 3. This is an important one. 1.3 repeating. Okay, thank you. No? Oh, 0.13. Okay. Okay. Let's go with this. This one feels right to me. Okay, step 3. What is it? Right. Okay, so what are the forces acting? Well, anytime you have a hinge, we have an unknown force vector that you can just think of as a component in the x direction and a component in the y direction. We'll see that these don't come into the calculation, but for this to be an accurate free body diagram, you have to put those in. So this is always how you're going to represent a hinge or a pin joint, or anything where the body can rotate freely around it. And what other forces are acting? The weight, yep. So that acts at the center of mass, straight down, and that has a magnitude of 2 times 9.81, so 19.62. Now there are a couple of ways. The next step is to calculate the moments. And there are a couple of ways to do that. One way is to move this force along its line of action until the force is perpendicular to the row vector. In this case, that means moving the weight up to here. Okay. Then the row vector is horizontal and the force is vertical. Okay. And so that says that the moment produced by the weight is equal to 19.62 times the distance from the about point to the force once you get it to the right spot, you know, that perpendicular distance. So what's the perpendicular distance from this point to that force or to its line of action? 0.2, yep. And the last thing you have to do is figure out, since this is our about point, imagine it's free to rotate around this point. Would this force make it rotate clockwise or counterclockwise around A? Clockwise, so is it positive or negative? Yep, so negative, and that's because it's clockwise. And we have to do this for every force. So what's the force produced by R, that reaction moment? Well, any force that acts at the about point or its line of action goes through the about point produces zero moment about it. Okay, I mean, you can think of, we're already in a place where that force is perpendicular to the row vector. That distance is zero, and so the moment is zero. You can't turn anything by applying a force to the hinge. Okay. And so this moment comes out to be zero, and that's why, you know, I said those forces weren't going to come into this. And so MA net then is just equal to negative 3.924. Bam! And the units are Newton meters. Who's still with me? 2, perfect. Step 5. Ooh, here's where the good news comes. So this was step 3, this was step 4. Step 5, no Newton's second law. Anytime there's a fixed point, you can skip Newton's second law. Okay, we can get all the information without it. And so now we'll go straight to the moment equation. Rn2L. And that says the net moment about A, negative 3.924, is equal to 0.13 repeating times alpha. And so the angular acceleration is, can someone divide that? Negative 30.18 radians per second squared. So it has an angular acceleration that's clockwise. That makes sense if you think about, and also so in this example, let's say it starts at rest. I should have said that before, but I did not. Okay, so now what we have the angular acceleration. And now we want to calculate the acceleration of this point as it rotates around this. You can think of that, this is in a circular motion around the hinge. Okay, and we know we have a clockwise angular acceleration of 30.18. Since it starts at rest, there's no angular velocity. And so based on this direction of the angular acceleration, what's the direction of the tangential acceleration? Down, yep. So this is a tangential. Centripetal is toward the center, but we're going to see that 0 because there's no angular velocity. So now we're back into stuff that we know well. We've done problems like this before. So the magnitude of the tangential acceleration is the angular acceleration times the radius to the center of the circle. So that's 30.18 times that distance from the center of the circle to the point we want is 0.4. Can someone multiply that? 12.07 meters per second squared. The centripetal acceleration magnitude is omega squared times r. That's 0 squared times r, so that's 0. And so the total acceleration of that point B is the tangential acceleration. And that is a magnitude of 12.07 acting in the negative y direction. And so that's 0, negative 12.07. Right. So yeah, think of the angular velocity. The angular velocity is not affected by forces at that instant. If you keep applying forces over a length of time, it'll build up velocity. But so if you say it starts at rest, then that's the velocity at that instant. Velocity doesn't change in a single instant. Only acceleration changes in a single instant due to forces. Okay. So what if I had said that instead of starting at rest, it started with a certain angular velocity, then that would just be part of our circular motion calculation. And we calculate the centripetal acceleration. And our total acceleration wouldn't just be down. It would also have a component towards the center. By the way, look at the magnitude of that. It's sort of an interesting thing. This thing is just acting under the influence of gravity. But as you get out toward the edge, you have points accelerating downward with more than the acceleration of gravity. And as you get closer to the hinge, the magnitude of that acceleration is smaller until you get here and it's not moving at all. Any questions? Okay. Well, I think I'm just going to stop there, and I'll give you a bunch of problems pretty similar to that. And if you want to, look at them tonight or whatever, and If they look like you can handle them, feel free to just leave after the post-test tomorrow. And if they look like you'd like me to help you out with some of them, stay afterwards and we can talk about it. Okay, bye.